Let's see some examples of how to create models using Scikit-Learn. In this video, we are going to create 3 classification models for our iris dataset. These models will be created using the logistic regression algorithm, the decision tree algorithm, and the k-nearest neighbors algorithm. Let's start with logistic regression. Logistic regression is a probabilistic classification algorithm. If we have a trained logistic regression model and then we provide it feature information for a new observation, the output that we get from the model is not one specific class, but instead a probability distribution over all of the possible classes. For example, once we've trained a logistic regression model on our iris dataset, if we feed it feature information for a new flower, so in other words, sepal width, sepal length, petal width, and petal length for a new flower, what we would get back out is an array with 3 probabilities. Maybe we would get something like a 20% probability that the flower is setosa, a 30% probability that it is versicolor, and a 50% probability that it is virginica. In that case, since virginica has the highest probability, we would classify the flower as being virginica. Okay, so let's see how to create a logistic regression model. We start off by creating an instance, by importing the logistic regression class. That is contained within the linear model module of Scikit-Learn. So we can type from scikit-learn.linearModel import logistic regression. So we now need to create an instance of this logistic regression class. So we do so here. We create an instance of logistic regression and store the result in model 1. Notice I have this argument assignment here, solver equals lbfgs. Let me come back in a moment and explain the purpose of that. But for now, just note that here we are creating an instance of a logistic regression classifier, but it has not yet seen our training data, and so it is an untrained model. So in the next step, we will train the model by calling its fit method and then passing the training data, the training features, as well as the training label. At this point, we now have a trained model. Model 1 will be capable of generating predictions. Let's see how we do that. So I'm actually going to create a new observation for which we are going to generate predictions. So here I am creating a variable x1 to store the 4 feature values for a new flower. So we have 4, 2.5, 2, and 0.5. These correspond to the various lengths and widths of the sepal and petals. Notice that I have created this as a list of lists. Really, it's a list containing a single list. The reason for that is when we provide this object to the predict function, it expects the input to be a 2-dimensional structure. This is actually useful because, well, in this particular case, we're only generating a prediction for a single observation. But if we had 5 or 6 or 20 new observations for which we wanted to generate predictions, we can store those as rows in a new object and feed them all to predict at the same time. We'll see an example of that in a moment, but for now, just note that the input for predict needs to be a 2-dimensional structure. So in this case, a list of lists. So now we can generate a prediction for this flower by passing its features, x0, into the predict method of our trained model. So we're going to store the results of that in an object called predict0m1. Okay? So we're generating a prediction for observation 0 according to model 1. Then we will print that prediction. So this will actually print out a specific species of flower, setosa, versicolor, or virginica. But as I mentioned before, logistic regression models actually output, the thing that they directly output is a probability distribution. It's often useful to see that probability distribution so that we have a sense as to how confident our model is in the predictions that it has made. So we can actually access that. We can access that by using the predict proba method of our model. So we would use predict to get an actual class and predict proba to get the probability distribution. So the format is still the same. model1.predictProba, and then we give it the feature values for the new observation. And then we're going to store the results in prob 0, M1, and then we print the results rounded to 4 decimal places. When I run that cell, we see that this particular flower was classified as a setosa by our logistic regression model, and we have the following probabilities. The model predicted a roughly 60% probability of the flower being setosa, 40% of it being versicolor, and 0% chance of it being virginica. Basically, these are the probabilities here are for the classes as listed in alphabetical order. So setosa, virginica, and then, setosa, versicolor, and then virginica. So our model predicts a 60% chance that this particular flower is setosa. Before I go on to decision trees, let me talk a little bit about this solver equals LBFGS. So a lot of machine learning algorithms will find, when you train a model, when you train a machine learning model, there's typically an iterative process where some algorithm searches through all of the possible models of that type. So in other words, in this case, all of the possible logistic regression models, and it finds the one that best fits the training data provided. We'll talk more about that later, but the idea is that there is some iterative process through which the model learns from the training data, and in that process of learning, it sort of converges down to the optimal model for the training data. And there are many different optimization algorithms that can be used for performing that step. Now, the good news is this is all performed kind of under the hood by Scikit-Learn. We don't typically have to think that much about what sort of optimization algorithm is being applied. However, due to an update in Scikit-Learn, the default solver of logistic regression was changed recently to LBFGS. And to let people know that that is the case, if you don't include this line specifying the solver as LBFGS, you actually get a warning message alerting you to the update. That warning message is a little unsightly and it clutters up your output. So to suppress it, we will actually explicitly set the solver as LBFGS, and then Scikit-Learn will know not to output that warning. So this is really just sort of a technical thing that we are doing to, this is not really a hyperparameter that determines how the model behaves. This is just something we do to kind of suppress a warning that would otherwise be output. Okay, so moving on, we will now consider decision tree models. So a decision tree algorithm employs a divide and conquer strategy to create a rules-based model for making classifications. We'll discuss this in more detail later, but the idea is the algorithm will look at the entire data set and say, you know, we can get the best classifications like for this data set if we first look at perhaps petal width. And then we're going to make a prediction that all observations with the petal width below this amount are setosa, and all above that are virginica. But then it might say, okay, as a second level, all of those that we classified as virginica, we're going to further split that based on sepal length. And then we're going to divide those observations based on sepal length, and then on one side we're going to classify as a certain class, and on the other side we're going to classify as a different class. So there's this sort of iterative process of splitting your data set up by features. And then this essentially amounts to a bunch of if-else statements that will ultimately boil down to a single classification. Okay, so let's see how to create a decision tree classifier. We import the decision tree classifier class from the tree model within Scikit-Learn. Now, there is a certain amount of randomness that is involved in training a decision tree classifier. It is not a deterministic process. In other words, every time you train a decision tree classifier on a particular training set, there is a small chance that you will get a different set of rules. We want to have some reproducibility for our results. So to make sure that our decision tree classifier trains the same way each time, we are going to set a seed. Again, it does not matter what seed you set, just as long as you set a consistent seed. You can choose a value different than 1 and then run this code, and you will get consistent results every time you do run it, but they will be a little bit different from mine since I did set a seed of 1. Okay, so I now need to create an instance of the decision tree classifier. I will do that and then store the results in model 2. Now, decision tree classifiers have many different hyperparameters that we can specify. We are going to specify one of these hyperparameters called max depth. We're going to set that equal to 7. Basically, all this means is this is the maximum number of rules that the classifier will consider on the way to making a classification. So maybe it will follow a sequence of, is petal length less than this? If so, then you go down this branch. Is sepal width greater than this? If so, you go down this other branch. So on and so forth. This particular tree will consider at most 7 of those possible if statements. Okay, so now that we've created an instance of the decision tree classifier, we will train it by calling the fit method on the training data. At that point, model 2 will be a fully trained model that we can use for generating predictions. So here we will generate predictions using the predict method, and I will use the same observation that we used for logistic regression. So I'm going to use a decision tree classifier to predict the class of that particular observation. Decision trees work a little bit different than logistic regression. By default, the output of a decision tree algorithm is a particular class, Setosa, versicolor, virginica. However, they are also capable of estimating a probability distribution. So we can access that as well by calling the predict proba method of the model, passing it the new observation, just like we did with logistic regression. So if I run this, I see that our decision tree classifier has classified our our observation as Setosa, just like the logistic regression algorithm did. And the probability distribution it gave was 100% Setosa, 0% versicolor, and 0% virginica. So this model appears to be much more confident that the flower is in fact a Setosa than the logistic regression model was. It only predicted a 60% chance of the observation being a Setosa. However, I want to warn you against putting too much stock in the probabilities generated by a decision tree classifier. We will see why later, but these numbers are typically a little less reliable than what is produced by a logistic regression model. The probability estimates produced by a logistic regression are much more sophisticated than the ones created by a decision tree model. Okay, so next let's move on to k-nearest neighbors. K-nearest neighbors is a distance-based algorithm. There are lots of different KNN models that you can create, and they are all distinguished from one another by a choice of the hyperparameter k. In this particular case, we will be looking at a 15 nearest neighbors algorithm. So when we want to classify a new observation based on a 15 nearest neighbors algorithm, what we would do is find the 15 observations within the training set that are nearest to the new observation. And we mean nearest in the sense of calculating distance based on the features, like how different are these two observations based on their sepal width, their sepal length, their petal width, and their petal length. And then we combine all of that into one distance. So when classifying a new observation, we find the 15 observations that are closest to the new observation, and then we let them vote on which class the new observation should be classified as. Okay, so to create a k-nearest neighbors classifier, we import k-neighbors classifier from the neighbors module within Scikit-Learn. We create an instance of the model, specifying the hyperparameter k, or as it's known in Scikit-Learn, in neighbors, number of neighbors. We specify that to be 15. So then we have an untrained model called model 3. We then train it by calling the fit method, providing it the training data. So we now have a trained model in model 3. Then the syntax for generating predictions is exactly the same as before. We can call the predict method, passing it the new observation. and this will tell us a specific predicted class. Once again, just like with logistic regression in decision tree algorithms, our trained KNN model also is capable of generating probability estimates. So we can see those by calling the predict_proba method. Okay, let's run this cell. And we see that just like the other two models, the k-nearest neighbors model predicts that this new flower is in fact a setosa. And looking at the probability distribution it generates, it is 100% confident that the flower is in fact a setosa. And it has a 0% estimate that it is versicolor and a 0% chance that it is virginica. Now, again, I want to point out that you should not put a lot of stock in these probabilities. Just like with decision trees, the probability estimates produced by a k-nearest neighbors algorithm are not quite as sophisticated as the ones generated by logistic regression.